Welcome to Spring LIB.
Okay, so we've got these two blocks that are going to be colliding, where we have the 2 kilogram block will be sliding into the 4 kilogram block with a speed of with an initial speed of 1 meters per second, but it will slow down as it approaches it due to the coefficient of friction. So the thing we're looking for is how far apart these two blocks will be after they collide, which means we need to find the speed of the 2 kilogram block before the instant before the collision, the speeds of both blocks after the collision, and then we can use those speeds to figure out how far they travel and the difference between those two distances. So to start, we need our initial velocity. So the initial velocity of our block can be given by this equation here, where we have final velocity is equal to the initial velocity plus 2 times the acceleration times the change in distance, delta x, or s if you're used to that terminology. But we have and this acceleration we can figure out using the coefficient of friction, because the force of friction is going to be slowing this thing down, so that's going to be equal to mass times acceleration, which is just Newton's second law, and it's also mu times the normal force, or mg. And so we've got an m on both sides, so we can cancel that. So we have a equals mu times g, and we are told to use 10 for g, so that's going to be 0.2 times 10, or 2 meters per second squared, as the acceleration, the deceleration, I think, is going to feel. So the final velocity is going to be equal to the square root of this whole side, which v naught is 1 meters per second squared, and 1 squared is just 1. And then we have 2 times 2 times 16 centimeters, or 0.16 meters. And thus, we're going to get this velocity as .6 meters per second. So this is the velocity that block 2 is going to strike, or sorry, the 2 kilogram block is going to strike the 4 kilogram block. So after they collide, we're going to have to figure out their velocity. So we'll use conservation of momentum. The momentum before is going to be the mass of the 2 kilogram block times its speed of 0.6. The momentum after is the momentum of the 2 kilogram block times its speed, we'll call that v1, plus the 4 kilogram block times its speed, we'll call that v2. And so we've got 2, so this will be a 1.2 on this side. This is kilogram meters per second. And actually, before we do that, let's divide both sides by 2. So if we divide everything by 2, we'll end up with 0.6 is equal to v1 plus 2v2 on this side. And then from our collision equation, we know that v2 minus v1, the difference in their speeds after the collision, will be equal to their difference in speeds before the collision. And before the collision, the difference in speeds is 0.6, because that's all that we have there. So if we then plug, so we get v2 is equal to 0.6 minus v1. We plug that into this equation here. or rather, if we just subtract these two equations, we should get actually, let's step that back real quick. And instead of subtracting, we're going to add these two equations together because we got a negative v1 and a v1. And if we add these together, we're going to get 0.6 plus 0.6, or 1.2. V1s will cancel, and we'll end up with 3 v2. If we solve that for v2, we should get 0.4, or 1.2 divided by 3. So v2 is 0.4 meters per second. That is the speed of the larger block. And then to figure out how far the larger block traveled, we can use the work energy theorem, because we're going to have the work done is going to be equal to the change in kinetic energy, where the work done is the friction force, or mu times the normal force. And that's going to equal 1/2 times the mass of the block times the velocity squared. Well, there's mass on both sides, so those cancel out. And then we can find, this I forgot to mention is times the distance. So if we solve for distance, we're going to end up with v squared, v2 squared, over the coefficient of friction times g times 2 because of this 1/2. So in this case, our velocity was 0.4, so we square 0.4 divided by 0.2 times 10 for g times 2, and we should end up with a distance of 4 centimeters. Now for the 2 kilogram block, we can use this velocity here, plug it into either of these two equations. Let's just plug it into this one here. And so we're going to have this equation. If we solve this for v1, v1 is going to be equal to 0.6 minus 2 times v2. And v2 was 0.4. So 0.6 minus 2 times 0.4 is 0.6 minus 0.8. So we're going to end up with negative 0.2 meters per second for the smaller block. So it has recoil and is moving backwards. And then for this one, we're going to do the exact same thing we did here. Work is equal to the change in kinetic energy. Forgot to put the delta there. So we have mu times mass times gravity times the distance traveled. That's going to equal 1/2 times mass times velocity 1 squared. Masses are going to cancel. And if we solve this for the distance traveled, we get v1 squared, or negative 0.2 squared. So we'll just have to remember that this is bouncing back. So 0.2 squared, negative 0.2 squared. So that negative sign is going to go away, but this is bouncing back. And then over mu times g times 2 because of that 1/2. And so our distance here will be 1 centimeter, 0.01 meters, 1 centimeter, but in the opposite direction. So we've got the larger cube moving 4 centimeters forward and the smaller cube moving 1 centimeter back. So the difference in their travels, the distance apart that they are, is 5 centimeters of separation.